This is a beautiful question from rotation. It says a rod is leaning vertically against a smooth wall, which also lies on the smooth horizontal floor. So here is the diagram. Initially, the rod is lying straight against this vertical wall. And it's smooth, so here mu is equal to 0, and which also lies on the smooth floor, so here also frictionless surface is there. At what angle with the wall will the rod loses contact with the wall if lower end of the rod is gently pushed? So this lower end of the rod is gently pushed, so what is the angle with the wall at which the rod is going to lose contact? We have to find this one. So let's say at some angle the rod is losing contact with the wall. Let's say this angle is theta, theta we have to find, and here the normal reaction force is going to be 0. This normal with the wall is going to be 0, which we have to find, right? So let's see how we are going to do it. First of all, in order to solve this problem, first step is going to look at the trajectory followed by center of mass of the rod. So we can straightforward see that the center of mass's trajectory is going to be circular. How? Because this is the midpoint, and also if you look at this distance, this distance is also going to be the same, that is L over 2. Let's L be the distance, L be the length of the rod, so this distance is also going to be L by 2. If we consider this distance is L by 2, so of course this is going to be circular because you are joining the midpoint of the rod to descend to the vertex. So this will be L by 2 from geometry. So of course this is going to be quarter of a circle because as the rod falls down, and finally the rod is going to be in the horizontal position. So here let's say this is xy. So we can say x square plus y square is equal to L by 2 whole square. This will be the equation of a circle. Next thing, let's say at this instant, omega be the angular velocity of the rod. So omega about this center of mass and omega about this point O will be same, because this angle is also going to be theta. So d theta over dt will be same about anyone, right? So omega about the center of mass and omega about this O will be same. Fine. So here what I'm gonna do is apply conservation of energy. This is our one equation, conservation of energy. But how will you apply this conservation of energy? One way to apply this conservation of energy is to think of the instantaneous center of rotation. This point is instantaneous center of rotation, and you can directly write the kinetic energy of this rod, because this rod is undergoing rotation as well as translation, right? Because center of mass will have this velocity vc also. So you can write the kinetic energy of the rod is equal to half I c omega square plus half mvc square, or directly you can write half I omega square. I'm taking I about this ICOR. This is what I. And of course, we can see that instantaneous center of rotations I is also equal to I is equal to ml square by 12 plus What is this distance? This distance is also gonna be ml over 2 whole square according to parallaxes theorem, and it comes out to be ml square over 3. This is the moment of inertia about ICOR. Now we have this kinetic energy, and loss in potential energy will be equal to mg times, you can see that initially L by 2 and finally this is L by 2 cos theta. So directly you can say the loss in potential energy will be mg times L by 2 minus L by 2 cos theta is the height with which the center of mass falls. This is the loss in potential energy is going to be equal to the kinetic energy, which is equal to half I omega square. I is ml square over 3 times omega square, and from here we will be getting our omega square, the value of omega square, mass gets cancelled. So this becomes GL over 2, 1 minus cos theta is equal to omega square over 2 times 3 times, let's say, L square. We have this omega square, we have, let's say, omega square is equal to 3g 1 minus cos theta over L. This we have. Let's say this is equation number 1. Now another equation we want to find is torque is equal to I alpha. Next equation we have to find is tau is equal to I alpha. And what is tau is equal to I alpha? You have to take torque about instantaneous center of rotation, not about the center of mass. You can take net torque about center of mass, but of course the normal reaction force offered by this is going to come. So again, some tedious job will be there. So I'm going to consider net torque about ICOR. That is, if you consider this ICOR, this normal, let's say N1, the torque of N1 will be 0 because N1 is passing through ICOR. So you can just take the torque of mg about ICOR, that is mg times this distance, perpendicular distance, is L by 2 sine theta, right? Because this angle is theta, this angle will be 90 minus theta, and this distance will be L over 2 sine theta. So mg L by 2 sine theta is equal to moment of inertia ml square over 3 times alpha, and we get this alpha is equal to 3g over 2 L sine theta. This is alpha we have, and omega square we have this. Now we have to think another condition, like normal reaction force is equal to 0. We have to think about this condition. Under normal reaction force is equal to 0, what equation we can make? Look at the center of mass. Center of mass is traveling in circular motion, right? So we can see that since normal reaction force is equal to 0, so in horizontal direction net force is equal to 0. So we can also say that from F is equal to MAC, mass times acceleration center of mass, net force is equal to MSE. We can also say that acceleration of center of mass in x direction is equal to 0. That's very important. Now look at this condition. If you consider the center of mass is moving in a circle at this position. Center of mass has like alpha times L by 2 is the tangential acceleration, and another component is omega square times L by 2. Omega square times L by 2. Now these are the two components of the acceleration of center of mass, right? One is the vertical, one is the normal component and another is the tangential component. Now if you take its component in x direction, so directly you have to take its component omega square L by 2, component of omega square L by 2, which is, this angle is theta, right? So this will be 90 minus theta. So we can say omega square L by 2 sine theta, component of omega square L by 2 in this direction, and this angle is 90 minus theta, so this angle is theta, vertically opposite angle, and this must be equal to alpha L by 2 cos theta. So we can say that omega square sine theta is equal to alpha cos theta. We have these three equations: first equation, second equation, and the third equation. From all these three equations we can easily find angle theta eliminating alpha and omega. So let's see. I'm going to use equation 1 and 3 to eliminate omega square. So omega square, put the value of omega square in equation 3. So it's going to be 3g into 1 minus cos theta over L times sine theta is equal to alpha cos theta. Now I'm plugging the value of alpha from equation 2 back into equation 3, that is 3z over 2L sine theta times cos theta. This is from equation 1, 2 and 3. So we have like 3g gets cancelled, L gets cancelled, sine theta also gets cancelled. We have like 1 minus cos theta is equal to 1 by 2 cos theta, and finally we have cos theta times 1 plus 1 by 2 is 3 by 2 is equal to 1, and we have cos theta is equal to 2 over 3, so theta is equal to cos inverse of 2 over 3. This is the final answer. Hope you understand it. Make sense? Thank you.